All right, let's talk about the monotone convergence theorem. I know, it sounds super intimidating, right? But stick with me because this is actually one of the coolest and honestly most intuitive shortcuts in all of calculus. By the end of this, it's going to feel like total common sense. You'll see.
So, to get started, let me ask you a question. Imagine you're trapped in a room. You can only walk forward, always forward. You can never turn back. But there's a wall right in front of you. Where are you going to end up? Pretty obvious, right? Just hang on to that thought for a second. This little thought experiment has a great name, the ceiling trap analogy. So let's tweak the scenario a bit. You're on a staircase now. Rule number 1, you are always walking upstairs. You never ever take a step down. Got it? Okay. Rule number 2, there's a ceiling right over your head. You can literally feel it just inches away. So you're always going up, but you can't go up forever. What has to happen? Well, you've got to stop somewhere, right? You're going to end up right at that ceiling, or at least on the very last step you can possibly take. You must stop.
Okay, so here's how we're going to break this down. First, we'll stick with this ceiling trap idea. Then we'll translate it into the big theorem itself. After that, we'll look at how to prove its two parts, monotonicity and boundedness. And finally, we'll see why this whole thing is such a game changer. All right, let's get to it. The big theorem, turning our analogy into math. You know what's so cool about this is how perfectly our little story maps onto the real math terms. Always walking upstairs? Well, in calculus, we call that monotonic increasing. It just means the numbers in our sequence are always getting bigger, or maybe staying the same, but they never go down. And that roof overhead? That's called being bounded above. It means there's a hard limit, a number that the sequence can get close to but never ever cross. So what about the final part? You must stop somewhere? Well, that's the big one. That's convergence. It means the sequence has to be heading towards some specific finite number, and that's it. That's the whole theorem right there. Every bounded monotonic sequence is convergent. If you can show those two things, that you're always moving in one direction and that you have a wall or a ceiling stopping you, then you are guaranteed to be heading towards a limit. It literally has no other choice. Okay, so now for the practical part, proving monotonicity. It's great to know the rule, but how do we actually show a sequence is always increasing or decreasing? Let's find out. Let's take a look at this sequence here. You plug in n equals 1, you get a half. Plug in n equals 2, you get 2/5. Plug in n equals 3, you get 3/10. Now, it kind of looks like the numbers are getting smaller, right? But in math, kind of looks like it isn't good enough. We have to prove it for every single term, all the way to infinity. So how do we do that? Well, we can pull out our first tool, the derivative test. The trick is to just pretend our sequence is a function of x instead of n. And as you know from calculus, the sign of the derivative tells you everything you need to know about whether a function is going up or down. So we'll rewrite our sequence as a function. F of x equals x over x squared plus 1. Now, time for a little bit of fun with the quotient rule. You remember that one, right? Low d high minus high d low over the square of what's below. When you grind through the algebra, you end up with this nice, clean expression for the derivative. Now let's analyze this thing. Look at the bottom, the denominator. It's something squared, so that part is always going to be positive, no question. Now look at the top, the numerator. As soon as x is bigger than 1, which it will be for our sequence, that 1 minus x squared part is going to be negative. So what do we have? A negative divided by a positive. The whole thing is negative, and a negative derivative means our function is always decreasing, which means our sequence is monotonic decreasing. Boom. Done. Okay, that worked great. But what if derivatives are a huge pain? Or worse, what if you have something like a factorial in your sequence? I mean, what even is the derivative of n factorial? Yeah, no thanks. We need another way. So, how about this one? Is n factorial divided by 2 to the n monotonic? Yeah, trying to use the derivative test here would be an absolute mess. This is exactly where we need a different tool from our toolbox. And here it is, tool number 2, the ratio test. The idea here is actually really simple. Instead of a derivative, we just compare each term to the one right before it by making a fraction, a ratio. This trick is a lifesaver for anything with factorials or powers. Okay, let's walk through it. We just set up the ratio, the next term over the current term. Then you plug in the formulas, and this is where the magic happens. A bunch of stuff cancels out. The n factorial on the bottom cancels with most of the n plus 1 factorial on top.
The 2 to the n on top cancels with most of the 2 to the n plus 1 on the bottom. And when all the dust settles, you're left with something super simple, just n plus 1 over 2.
So what does this ratio even mean? Well, think about it. If the ratio of the next term to the current term is bigger than 1, that just means the terms are getting bigger. They're increasing. And for our result, n plus 1 over 2, well, as long as n is 1 or bigger, that fraction is going to be 1 or bigger. And there you have it. The sequence is monotonic increasing.
All right, part 1 down. We know how to prove something is monotonic. Now for the second piece of the puzzle, proving boundedness. How do we show that there is a ceiling or a floor?
Let's use a super classic example, 1 over n. You've seen this one a million times. The terms go 1, a half, a third, a fourth, just getting smaller and smaller. I mean, it really feels like it's trapped, doesn't it?
And finding the bounds is pretty straightforward here. What's the biggest this can ever be? Well, that happens right at the start, when n equals 1. The value is just 1. So that's our ceiling, our upper bound. What about the floor? Well, since n is always positive, 1 over n is always positive. It gets really, really close to 0, but it never quite gets there. So 0 is our lower bound. The sequence is totally bounded, trapped between 0 and 1.
And now we put it all together. This is the payoff, the convergence guarantee. We've done the hard work. Now let's see what we've earned.
Let's just go back to that core idea because it really says it all so perfectly. If a sequence is always increasing, that's monotonic, but stuck below a ceiling, that's bounded, it must converge. It simply has no other option. It's walking upstairs. It hits a ceiling. It has to stop somewhere.
And that's the whole point. This theorem gives you one thing, but it's an incredibly powerful thing, a guarantee. It guarantees convergence. It tells you for sure that a limit exists. And this is why it's such a brilliant shortcut. Think about it. Sometimes actually finding the exact number a sequence converges to is really, really hard. This theorem lets you skip that. It lets you prove that a limit exists without ever having to calculate what it is. It's a tool that proves the destination is real, even if you don't know the exact address. And honestly, in higher level math, just knowing a limit exists is often the most critical piece of a bigger puzzle. It's the foundation for your whole argument. It just makes you wonder, right? What other beautiful, powerful shortcuts like this are out there just hiding in plain sight? Thanks for tuning in.